Hello, good morning. So I gave kind of a long title to the presentation, a little bit technical too, but really what I'm going to talk about is the chaos that we face when we have multiple options. In fact, I think you all know in bioinformatics, as soon as there is a task, there is also multiple options. And this is very true for many cases, so you can think about protein folding, you can think about differential expression, or for instance, multiple sequence alignments. And the reason why there is multiple options is that there is no guaranteed best. So if there was one solution that is always the best one, then problem solved, and we have the solution. But the problem is that depending on which data we have, how much data we have, and what is exactly that we're after, then one solution may work better than the other. Now, in the lab, we do care a lot about multiple sequence alignments. And so why? So unfortunately, we all have been exposed to COVID times. So I think we all remember how it was, checking for the latest evolution of the virus. So we were checking, okay, has enough mutation been accumulated by the virus so that now the antibody is now not binding as well as it was before, and maybe it's not effective. The vaccines are not as effective. And exactly when you're looking after this, so when you're looking after regions that are being conserved, regions that are evolving, and trying to start tracing the evolutionary history, for instance, COVID, that's when you would start using multiple sequence alignments. Now, a little bit beyond COVID, if you think about it, evolution is nothing else than billions of years of nature's experiment. And this is so, so powerful. And MSAs happen to be a very compact framework to summarize this information. And this has been proven very, very useful. And you can think about AlphaFold 2, for instance. So this has risen quite a lot of interest in the community. Yet MSAs have quite an infamous aspect, which is they are very computationally complex. So they're NP-hard problem, and they have to rely on approximation, on heuristics. And lastly, in the last years, as we all know, there has been a lot of data production, and there are now these sequencing projects, like, for instance, the Earth Biogenome. They're generating a lot of data. That's very exciting, yet these methods are not really ready to keep up with this pace. Also, on another note about data production, now even AI is generating data. So now, we have all the structures of AlphaFold 2, and they're stored in a database. And factually, we can use them to now compute multiple sequence alignments as well. So it's an extra layer of amount of data that we have. Now, all of this together has resulted in this. So we have a lot of suboptimal solution. When I say suboptimal, it's the literal meaning. So it's not optimal solution. So this is just a screenshot of the beginning of the Wikipedia page. It's not necessarily the most reliable source, but we really have a lot of these solutions. So last year, we asked ourselves, okay, maybe we cannot have always the optimal solution, but is there one of these methods that is the safe bet, that is always the best across all of the other methods? So we tested it on different data sets. So now each line is a different data set, and the length of the line is the accuracy of the best performing method on that data set. So it's the best solution that we could get out of any method. Now, the real signal that I'd like you to focus on here is the color of the bar. So they're colored by the best performing method on that specific data set. So if we stop 1 second and we look at t-coffee regressive, so regressive is the green one. Regressive is one method that was developed in the lab, in the Notre Dame lab, by Evan actually, some years ago, and it's a great tool. It's really one of the best performing tool of MSA's large scale. Yet if t-coffee was to perform best across all data sets, this is how it would look like. But this is not how it actually looks like. The scenario is still very scattered. This is not to this t-coffee. If you look at it like the second dot, the green one, it's still showing that t-coffee is doing quite well in most data sets. But the point that I'm trying to raise here is that sometimes, even for great algorithms, for some data sets, some other algorithms will perform a little bit better. And so we thought, okay, we need to do something about this. And so we started by creating a collection of these tools. So we wanted a format that is deployable, reproducible, and standardized. And of course, we took NF core modules. So we started creating this nice collection of all these NF core modules. We call it a method hub because eventually these methods are all doing the same things. They're like just different flavors, but same input, same output. So once we have built this MSA method hub, we built a pipeline around it. So it's called NF core multiple sequence align. and you can just use it to deploy your favorite MSA method. Now, once you have multiple options, you are left with two things that you can do. Option number one, you can combine the solutions. So you can try to go in and check, okay, where are the solutions agreeing? Where are the solutions disagreeing? Are they telling the same story or are they telling me something different? And you can try to create a consensus solution. Or you can take a step back and you can just compare the solution and evaluate them. Now, the pipeline currently already does all of this. I will not go step by step into the pipeline because I want to mention a couple of other things. But so on one side, you can just use the pipeline as purely a deployment tool. So it's a production tool. You have your input, you want your favorite MSA, and you're set. But the vision that we have on this pipeline is a little bit more ambitious, and we are really thinking of this as a central place for the MSA community, either a central leaderboard, benchmarking, however you want to call it, but a place for the MSA community where whenever a new tool gets developed, it can be plugged into this benchmark, and it can just be evaluated and compared with the others. There's multiple reasons why this one is desirable. A couple of them is that first, building benchmark is also not super fun. Like I think the developers that are developing these tools, they don't really care about building the benchmark every time they want to publish a new tool. So you would just have to provide your tool in an NF core module and then the work is done for you. And second, not necessarily because one is a bad scientist or a bad person, but sometimes you can be biased when you build your own benchmark. So it's very important to have something centralized and unbiased. Now, so the pipeline is implemented, it's functional, but there's one thing that we did not like and we currently still don't like about how the pipeline is currently implemented. So currently the main workflow looks like this somewhat. So you have a bunch of if-else statements or channel branching, however technicalities, but the point is that every time that you want to add a new method, you have to go and modify the main pipeline code. But it somewhat does not really make sense because really you have defined the data flow, you have defined the pipeline logic, so why should someone go and touch the code whenever a new method is developed? So this led to this project that Julia is leading. She presented yesterday, I think many of you know her, so you know it's going to be good. And it's called NF class. So just to give you an idea. So first of all, as soon as you have a class, you need a definition. So you need to be able to define what's in the class, otherwise you have no class. So in this case, for a method hub, you would define it by same input, same output. And once you have a definition, what's also cool is that you can identify methods that belong to that class, right? So you can scan NF core modules and say, okay, these 10 methods belong to my class. And the second very important step that you want to have is that it needs to be operational. So you need to be able to plug it into your pipeline and access this method from the method hub and actually run them. So once you would have this class module, you would just be able to plug it into your pipeline, and after a compilation step, whenever a new method comes into the method hub, you are able to automatically run this new method without having to modify the pipeline code again. So this is stuff that is ongoing in the lab. Then one last thing, so dive in a little bit deeper into the code a little bit. So okay, you have your input FASTA file. I told you you can deploy different methods, and you can combine them into one consensus solution and evaluate all of them. So this framework is very good at telling you is which methods perform best on which data set. What this method cannot tell you, unfortunately, is the why. Like, why is method A better than method B? Which was the key feature that made method A better than method B? Now, we don't have a final answer on how to answer this question, but we sat down in the lab and thought, okay, how can we get a little bit closer, at least, to the answer of this question? So how we're doing it now, we're just deconstructing. The only way we could come up to kind of get closer to this, to the answer is like, okay, we need to tear down this algorithm in smaller components. In fact, usually tools are distributed in unified packages. But many times, at least for multiple sequence alignments, the tools are composed by sequential steps. So you have step number one and step number two. In the very specific case of MSAs, these two steps, the most obvious split of the MSA would be guide tree and assembly. So guide tree defines which is the order in which you're going to align the sequences, and assembly, it actually is aligning the sequences. So, and this is implemented already in the pipeline, but the idea and the vision is to say, okay, we need to tear this down in more and more granular components, so that once you have all of these little components, you can play with them and start to get a better understanding of which one was actually the important one. And here I'm just going to throw a thought, because we started with this by thinking, okay, we want to deconstruct these algorithms. But also then we thought, okay, why are we actually not constructing algorithms? Like, we are used to think about Nextflow as just a deployment tool for tools, for unified packages. But when we started this effort of like, okay, we're tearing down our algorithms to evaluate them, then we thought, actually, in many cases, there is no reason why we could not use Nextflow to actually develop some methods. I mean, there's reason why if you have a very small scale, but if you go with really large data sets, or we have divide and conquer algorithms, that's something that we are currently looking into. So I don't have anything to show you on this one, but it's something that we are working on, and if someone's interested, you can reach out to us. So I told you a lot about ideas and stuff that we are thinking about doing, but just to clarify, the pipeline is released, so you can use it. We have a bunch of aligners. We have sequence-based aligners. We have structure-based aligners. You can compare, you can combine the solution, you can evaluate them in a bunch of different ways. We also have a nice report, a shiny app in the end. So if MSA is your thing, maybe you can look into the documentation and you can check this out. The release is called Somos Rostro because this was Bjorn's idea. So, and because it's, so we work at the CRG, so it's the beach in front of CRG is called Somos Rostro, and now the idea is with every release is to go up in the north to Costa Brava. So then I mentioned quickly about NF class, so what's currently ongoing in the lab and that Julia is leading, and then how we are planning and playing around with deconstructing but also constructing algorithms in Nextflow. So big thanks to the lab, especially to Jose, Leon, and Ale, the 3 people conveniently clustered in the picture, and Igor, the one in the bubble up there, and to you for listening.
Thank you. That was a great talk. Really useful resource as well. Very interesting ideas on both the NF class and the idea of you seeing Nextflow as a way to construct algorithms beyond just orchestrating tools. It's very cool. A few questions. Have you considered something like adding a model stacking or machine learning approach to select the best method for a given data set?
We have not, but that's a very interesting one. I think it's, we're now still working on a very stable framework where we can play around with things, but that sounds actually very interesting because usually the benchmarks that you're running are very computationally expensive, so that's why for now we're just trying to build something very stable, and now that we have it, we are thinking about all of these extensions. So thanks for the idea to whoever gave it.
Yeah, I think they'll be happy to discuss it on Slack. Yeah. Well, there was one question asking of all the options, which one would you suggest for speed, which to me suggests the question of, are you evaluating strictly for accuracy, like scientific correctness, or are you also looking at the logistics of the tool?
So we do collect all information in the final report, so eventually you get both information, so scientific accuracy as well as basically the information that you will get in the trace file. The final CSV is a merged CSV between all of the accuracy, but also the running times and memory that was used. They were asking which one I specifically suggest, or no?
Which one would you suggest based on speed?
Based on speed, then I would go with something like either T-Coffee Regressive or FAMSA. I think that's 2 of the very fast one, or Muscle 5. I think they're all quite good. Yeah.
Well, thank you. Somebody also congratulates you on the naming scheme.
That's yours.
Very good. All right. Well, thank you very much. Great talk.